everyone. Uh, Yesterday in the last class we have solved the problem on reheat, which was very simple problem where we found only the change in enthalpy, then we calculated heat added and all. So today we will go one step ahead and solve a reheat problem, but slightly today we will calculate a few extra things, that is cycle efficiency, steam rate and quality of steam. So let's look at the problem. So here we can see the steam enters the turbine of a steam power plant operating at 150 bar. So this you can see it is 150 bar and 600 degrees Celsius. So this is our P1, that is the pressure P1 and the temperature 600 degrees Celsius. Obviously it must be a superheat, but we don't know for sure. You need to look into the thermodynamics data handbook where to come to know whether it is superheated or not. So first, this is the pressure P1 150 bar. So what kind of pressure it is? It is a boiler pressure. So obviously it is the higher pressure. Here if you read the question, the steam enters the turbine. So where does the steam is entering? It is entering from the boiler. If the steam is entering from the boiler, obviously it is the boiler pressure. So that is how we have to analyze the problem. And that is condenser pressure is 0.1 bar. So it is very clear P2 is 0.1 bar. It is the pressure inside the condenser. So next, if reheat pressure is 40 bar, so the reheat pressure is 40 bar. So in a normal reheat, Rankine reheat cycle, we reheat the steam. So to what point we are reheating is to 600 degrees itself. We will be reheating to 600 degrees itself, but the pressure will be 40 bar. The reheat pressure will be 40 bar. Determine the quality of the steam. What do you mean by quality? It is the X. It is the amount of the wetness or the moisture content in the steam is the quality of the steam. Next, then we will calculate the cycle efficiency. Cycle efficiency, we know W that eta is equal to W net divided by heat added. Then we will calculate the steam rate, that is steam rate is equal to 1 by W net into 3600. Try to always be careful here. Steam rate will be always in kg per kilowatt hour. So this you have to multiply that 1 by W net into 3600, so that to convert that kg per kilowatt second to kg per kilowatt hour. So we will move on to the problem. So we will analyze the problem. The condenser pressure is 0.1 bar. The condenser pressure is 0.1 bar. Boiler pressure is 150 bar. The stream entry point is 150 bar and 600 degrees Celsius. Obviously we can come to know whether it is superheated or not. This is 600 degrees Celsius. Be careful here. So 150 bar is superheated. How do you come to know about it? By going to the steam table. We look at the steam table and we note down the value of the saturation temperature at 150 bar. If you come to know, if you look at the steam table at 150 bar, saturation temperature is less than the given value. Here given value is 600 degrees Celsius, then it is a superheated, obviously. So there in a pressure based charge at 150 bar, the saturation temperature should be always less than the given temperature, then it is always a superheated. Here also look, if you go and look in the steam table 40 bar, at 40 bar note down the saturation temperature, it is less than 600 degrees Celsius, then it is superheated. So always the any given pressure, if the temperature is above saturation temperature, then it is a superheated steam. So the layout of the Rankine cycle will look somewhat like this. So the steam will enter, it is pumped from a 0.1 bar then into the boiler at 150 degrees Celsius, at 150 bar and 500, sorry, it is, how much is the pressure? If you look at the problem, it is 600 degrees Celsius. So slight mistake is there. So 600 degrees Celsius, it is 600 degrees Celsius, 600 degrees Celsius. Please correct this. So we can correct it. So we have corrected here, it is 150 bar and 600 degrees Celsius. So in the boiler, the steam will flow from the boiler into the first turbine, that is high pressure turbine. Then it gets expanded till 40 bar. It is expanded till 40 bar. So the pressure after expanding from 3 to 4 will be 40 bar. Now this 40 bar pressure steam is again taken and it is reheated to 600 degrees Celsius. So it is 600 degrees Celsius. Then this 600 degrees Celsius steam with 40 bar pressure will be again made to pass through another turbine known as low pressure turbine. So this low pressure turbine will expand the steam from 40 bar till where to obviously it is the final turbine or low pressure turbine, so it will expand the steam from 40 bar to zero point 0.1 bar. So it is again expanded till 0.1 bar. So there are two expansions. One is high pressure expansion from 150 bar to 40 bar, then from 40 bar to 0.1 bar. So note down this. In between these expansion there is something called as reheat, which is reheated. Here it is 150 bar 600 degrees Celsius, here it is 40 bar again 600 degree Celsius. So we have corrected few of the things, that is 600 degrees Celsius. Then later on, what we have analyzed now, the problem itself. So we have analyzed the problem. Now we will move on to solving the problem. Before solving the problem, we need to also analyze or write how to write a TS diagram. So our TS diagram is the basis for our solution to the problem. So we know the reheat Rankine cycle is the default one. It is the default diagram will be there. You need not worry about what lies where. Just you can draw the Rankine cycle reheat normal format, that is TS diagram. Here 1 to 2 is pumping, 2 to 3 is boiler pressure heat addition, then 3 to 4 is a high pressure turbine expansion, then 4 to 5 is reheat, then 5 to 6 is again low pressure turbine, then 6 to 1 is condenser conversion of steam into liquid. Then this process continues. So we'll name few of the things. So we can see here, this is our boiler pressure 150 bar 600 degrees Celsius. This is our the high pressure from 3 to 4 till high pressure from 150 bar to 40 bar, then reheated to 40 bar 600 degrees Celsius, then expanded to 0.1 bar. Then this is our liquid, completely liquid. We can note down the point, that is H1 is equal to HF at 0.1 bar. We have to use the WP, that is WP is equal to H1 minus H2, and find the value of H2. Now we will move on to the next. We need to find 1 and 2. This we will use here the Moliere chart to find H3, H4, H5 and H6, but we will use a steam table to find H1. So we will use the steam table, then use the pump formula and find the H2. So look here. So we can see here H1. So H1 is equal to HF is equal to 0.1 bar. Why? H1 is equal to HF because 1 lies on a saturated liquid line. So whenever anything lies on a saturated liquid line, then it is obviously it is HF. It is a pure liquid or pure fluid. So at a 0.1 bar, it is completely a fluid. So H1 is equal to HF at 0.1 bar. So you go to the steam table which I have given you, shared with you. So I will share it again if you want. So we'll go to the steam. So in a steam table which I have given you already, it is, the name is thermodynamics data handbook. So it is, we can look, this is a pressure based chart. So in a pressure based chart 0.1 bar, you note down the value of HF. HF is a pure, it is completely in a liquid form. Whenever something is in completely liquid form, you note down directly it is H1 is equal to HF at 0.1 bar. You note down the value H1. Now we need to find the next term, that is H2. To find the value of H2, we cannot directly note down the value of H2. We have to use this formula, pump work is equal to volume of the fluid, that is volume of the fluid at 0.1 bar into P2 minus P1. So what is the volume of the fluid at 0.1 bar? We have to go to the thermodynamics data handbook again. So we'll go to the thermodynamics data handbook. So 0.1 bar, what is the volume of the fluid? So it has the fluid is completely a liquid. So at 0.1 bar, look at here, it is volume of the fluid. Volume of the fluid at 0.1 bar, volume of the fluid is 0.00 1010. So we will note down this value. So after noting down this value 0.001010, now look at the note down the pressure. So this is P2 minus P1. What is P2? P2 is, it is 150 bar minus zero point 0.1 bar. So it's the difference of the pressure. So note down the P 150 minus zero point 0.1 multiplied by 100, convert the bar into kilopascal. So you note down the volume work done by the pumping work 15.13 kilojoule per kg. Next you need to, you know already the pump work is 15.13. We know the H1, so you need to find the H2. So H2 is 206.9. So by now we have found the values of H1 and H2. Now we need to find the right part of the diagram, that is H3, H4, H5, H6. How to find this? So there are two methods. One is table method, which is very lengthy. We need, if we use the Mollier chart, it will be very short for us. Once we know the Mollier chart, how to use it, then everything will become very simple. So to find H3, H4, H5 using Mollier chart, we first of all will analyze the problem and write a Mollier chart. So this is H enthalpy, this is entropy. Enthalpy, we can note down the values. So H3, somewhere it will come here, 3, that is 150 bar and 600 degrees Celsius. So here 600 degrees is not given, line is given, but there will be a line 600 degrees Celsius, 150 bar line and 600 degree line will be there. So wherever two lines meet, 150 bar line meets with the 600 degree line. So when the point at which these two lines meet is the value of H3. Now the 150 bar, we already know that 150 bar is high pressure steam expands to 40 bar, that is to another pressure, that is it expands to 40 bar. So if it expands to 40 bar, 150 bar to 40 bar, so you need to draw a straight line, because expansion is an isentropic process, is in a straight line. So 3 to 4, it expands to a straight line. So you note down the value of H4. So you note down the value of H4. So we get H3, we get H4. So afterwards what you do is you reheat. Look again, you revise, keep recalling, reheat from a 4 to 5. Whenever we reheat, what will happen is 4 to 5. We reheat, we have to follow the 40 bar line. We follow the 40 bar line. Where do we stop? We stop at a 600 degrees Celsius. Where 40 bar and 600 degrees Celsius meet is the H5. So we note down the value of H5. So after noting down the value of H5, what we have to do is note down the value of H5, that is enthalpy H5. Next, what is the next process? The H5 in a low pressure turbine, from 40 bar to 600 degrees Celsius, it will expand till H6. So H6 is what? 0.1 bar. The expansion takes place from 40 bar to 0.1 bar degrees, 0.1 bar pressure. So expand. So you note down the value of H5, enthalpy H5, then you note down the value of H6. So H6, we know H3, we know H4, H5, H6. So if we know all the H4, H3, H4, H5, H6, we can also calculate the value of turbine work, H3 minus H4, H5 minus H6. Pump work we already know, heat input is H3 minus H2, H5 minus H6. To find all these things, we need enthalpies. To know these things, we need to use the Mollier chart, because we are solving by using Mollier chart. We will go to the Mollier chart diagram. So we can look here. So what is our first point? So we need to find the value of H. So we know that at 150 bar and 600 degrees Celsius, we need to note down the value of H3. So to note down the value of H3, we go to the Mollier chart. So after going to the molar chart, there will be a line called 150 bar line. So we already know the molar chart. This is the enthalpy. This is the enthalpy. We can use both the lines at the left line or the right line, and this is the entropy, the x-axis. So there are pressure lines. So this is the pressure lines. This is the pressure. 0.202 bar, zero point 0.1 bar, 0.3 bar, 50 bar, 60 bar. This is the pressure lines. Then these are the temperature lines. You can see here the inclined lines are the pressure lines. So this is 800, 600, 500 degrees Celsius. These are the pressure lines. So the pressure lines are also there. The bar lines also there. The pressure lines are also there. Temperature lines also there. So the pressure lines 100,000 bar, 600, 800 bar, 600 bar, 500 bar, 400 bar, 300 bar, and there is a temperature line 700 degrees Celsius, 650 degrees Celsius, 600 degrees Celsius, 550 degrees Celsius, 500 degrees Celsius, 450 degrees Celsius. All these things are there. So to find the first point H3, we need to know lock on to the 150 bar line, which is the 150 bar line. This is the 150 bar line. So you look here, it is 150 bar line. Just confirm whether it is a pressure only, because you should not get confused with the pressure bar line and temperature bar line. So it is bar line. So this is a pressure bar line. So how much is the pressure? 150 bar is the pressure. So this is the 150 bar. What is that? This is a black line, but I have highlighted, I have made it colored with the yellow color. So this, you can see the yellow color is there. So yellow color is the 150 bar line. It meets with a 600 degrees Celsius. So 600 degrees Celsius is another line. I have colored it with red color. So wherever the 600 meets with the 150 bar, it is the lock on. This is the H3. You note down the H3. How do you note down the H3? You can go to the left part, because it is in my chart as a little bit torn out. So I'll go to the right part. So if I go to straight line, we can note down the value. It is how much is the value? Each graduation represents 20 kilojoule per kg. So it is 3580, somewhat approximately it is 3580. You can be more precise in your chart. So use this chart and exactly you calculate the value of H3. Next, what happens in a high pressure? This is the boiler pressure. The steam expands from high pressure 150 bar, 600 degrees Celsius to a 40 bar. So it is an isentropic expansion. So it will be a straight line. Draw a straight line. Note down the value of and the straight line should intersect with 40 bar pressure line. Look at the 40 bar pressure line. It will be coming from the top also. You can take down, or bottom. See, from the bottom I am taking 40 bar pressure line, or you can take it down from the top 40 bar pressure line. So at 2 points the pressure is noted down in the bottom and the top. So you move along, the straight line intersects with 40 bar, you mark on, lock on. This is your point. Now move to the left or the right, both things are same. So you move to the left, I am moving to the left. What is the value? Each graduation represents 20 kilojoule per kg. Next, what is the first? 20, 40, 60. So 3160 is our H4. So you note down the value of H4. After noting down the value of H4, what we have to do is, we know now the expansion has taken from high pressure 150 bar to another pressure 40 bar. This is a high pressure turbine, and the expansion takes place through a higher pressure. Now 40 bar pressure, the steam here will be reheated again. How do we reheat? To reheat, we have to follow this curve, that is a 40 bar curve. This is be careful, this is a 40 bar curve. I have colored it. 40 bar curve moves to the top. Till where should it move? It should move it till the 600 degrees Celsius. This is the 600 degrees Celsius line. So 40 bar meets with the 600 degrees Celsius. So you note down, lock on. This is the note down the point, note down the exact point. Now move to the right or left, whichever you feel comfortable. Draw a straight line and lock on. This is the H5. So H5, each graduation represents 20 kilojoule. So 20, 3620, 3640, 3660, 3680. So my H5 value is 3680. Now what has happened? I have reheated the have reheated the steam to 40 bar and 600 degrees Celsius. So this is my reheat pressure and the temperature. Now it is now should be passed through what it should be passed through another low pressure turbine. The low pressure turbine, here it is an isentropic expansion, 40 bar 600 pressure, 40 bar 600 degrees Celsius to a low pressure of 0.1 bar. So what is the 0.1 bar? Is our low pressure. So how does the expansion takes place? The expansion is isentropic. Whenever something is isentropic, it is a straight line. You move down, draw a straight line till where, what is our condenser pressure? Our condenser pressure is 0.1 bar. So we have to move till the point called as 0.1 bar. How do you know which is the 0.1 bar? You look here on this line, there are pressure points. This is the 0.1 bar pressure. So you follow this 0.1 bar pressure till it meets the straight line. This is our lock on this. You note down this point, mark this point, and move to the right or left, whichever you feel comfortable. When you move along a straight line, you will note down the value of the final value, that is H6. H6 is 2400. So note down the value of H3, H4, H5, So we have noted down the value of H3, this is the H3, H4, H5, H6. So H6. So this is the high pressure line. This is the this is the high pressure turbine line. High pressure isentropic expansion. This is low pressure isentropic expansion. This is high pressure turbine. This is the low pressure turbine. This is the reheat. So I will tell again, this is the high pressure, this is the low pressure turbine. High pressure turbine, low pressure turbine, reheat. This is the reheat, 40 bar to 600 degrees Celsius. So 150 bar 600 degrees Celsius. Note down the 150 bar, take hold of the 150 bar line. This is the 150 bar line, here it will be there. So after noting down the 150 bar pressure, look here, 150 bar pressure. After noting down the taking the 150 bar line and noting down the 600 degrees Celsius, note down the H3. Next, taking the 40 bar line and joining the straight line with 40 bar, note down the value of H4. Next, taking down the 40 bar line, 600 degrees Celsius, note down the H5. Next, after moving down, straight down, noting down the value of straight line, meeting it with 0.1 bar line, you will get the value of H6. Another thing he has asked in the problem, that is the value of the dryness fraction. What is the dryness fraction here? You move along to this inclined line. This is the dryness fraction line. So dryness fraction, this is the value. What is the dryness fraction? It is the value of X, or moisture content. This is 9.9% dry, this is 0.85% dry. So if you move to the inclined line, you will see there it is 0.9% dry. This 0.9 dryness fraction is 0.9. You just move along, it is 0.91, I guess, because it doesn't lie on this line, but it is between 0.9 and 0.92. So note down the value of the dryness fraction. We have noted down H3, H4, H5, H6, H1, H2. We have calculated through steam table. Now we will go to the problem. So our problem becomes very simple, because we have use the Moliere chart. So we have noted down, so these are the approximate values. You please use your own chart and note down the exact values, H3, H4, H5 and H6. Now we know the formula. What is the turbine work? Work done by the turbine is H3 minus H4, high pressure. Then low pressure turbine, H5 minus H6. Pump work is H2 minus H1. Heat input is H3 minus H2 plus H5 minus H4. So H3 minus H2 is the heat input in the boiler. H5 minus H4 is the heat input during the reheat. What is the eta efficiency? W net divided by Q input, work done by the turbine to that of the heat input. WT minus WP. That work of the turbine minus work of the pump divided by heat added. Now we have to calculate, note down the values H3 minus H4. So we have calculated the value through Molière chart. H3, that is 150 bar 600 degrees Celsius. This is what H4. H4 we have calculated at 40 bar. Next H5. H5 what where we have calculated? We have calculated 40 bar and 600 degrees Celsius because this is the reheat. If you recall, then this is H6 is our final enthalpy at zero point 0.1 bar. So we calculate, we get the turbine 1760 kilojoule per kg and the pump work we have already calculated. So next Q heat input. Heat input to the turbine, heat input to the cycle is H3 minus H4. H3 is what? It is the, we already know it is the boiler enthalpy at H3, that is 150 bar 600 degrees Celsius, and H2 is what? It is the, this H2 value is wrong here. So H2 value we will note down. What is the H2 value? We have calculated here H2 values. So we have calculated H2. H2 is 206.9. So it is correct, 206.9. So H2 value is correct, sorry, 206.9. Next is H5 minus H4. H5 is the pressure. Where is the pressure? This pressure is where? H5. H5 is the pressure of the reheat. Sorry, it is the enthalpy of the reheat. That is at a pressure of 40 bar and 600 degrees Celsius. H4 is the, it is the value which we have noted wrong. So where is there? H4. H4 is the 40 bar point. So that is after expansion inside the high pressure turbine. So note down, substitute the values, calculate the heat input. After calculating, substitute WT minus WP. WT work of the turbine minus work of the pump divided by heat input. We will get the, multiplied by 100, we will get the 44.8% efficiency. This is the efficiency of the Rankine cycle, that is the reheat cycle. Then this is the extra point, we have to calculate steam rate, that is 1 by W net into 1, that is 1 W net, 1 by W net we already know 1744.9, and multiplied by 3600 to convert this kilojoule. Normally if you don't multiply 3600, it will be kg per kilowatt second. So convert to make this value into hour, we have to multiplied by 3600. So we multiplied by 3600, we will get the steam rate. So we'll revise this problem. What we have done is, it is a basic problem on a reheat. So there is a steam where in the boiler 150 bar and 600 degrees Celsius is the first point, that is the pressure is 150 bar and the temperature is 600 degrees Celsius. It is expanded till 40 bar. He will not give it as, but we have to understand by ourselves, because reheat is how much? 40 bar. So it is 150 bar 600 degrees Celsius to 40 bar. Then it is reheated to 40 bar. Reheat means obviously 40 bar will be at a 600 degrees Celsius. Then it is again expanded to 0.1 bar. So the default diagram will be this: 150 bar 600 degrees Celsius to 40 bar, then reheated to 40 bar 600 degrees Celsius, then expanded to 0.1 bar. No, use the Molière chart to calculate the H3, H4, H5, H6. Then use the steam table to calculate H1. Then after noting down the H1, use the formula pump work, WP is equal to H2 minus H1 to calculate the H2. So after that, substitute the values in the formulas and you can get the values. It is a very simple problem. So write down the same problem for the assignment in a sheet of paper and submit it on Wednesday. Thank you.